My name is Anthony Liguori. I'm a senior principal engineer in EC2, and I've been at Amazon for 4 years now, working on the virtualization platforms that power EC2. I'm also the lead of the Nitro project, which has culminated in the launch of our new Nitro hypervisor and the C5, M5, and i3 metal instance types. I'm really a virtualization geek at heart, so I'm going to be doing a deep dive into the evolution of our virtualization platform over the last 11 years with a focus on really explaining our new Nitro hypervisor. I intend on getting very technical, and I suspect this is going to be one of the more technical webinars, so we'll make sure to leave plenty of time at the end for any questions that you might have for us. At reInvent, we introduced the Nitro project, which is the name of our new virtualization stack that we launched with C5, M5, and i3 metal. In this webinar, we're going to walk through what the Nitro project is and how it relates to these new instance types. But to really understand the Nitro project, we need to step back a little bit and really do a dive into what virtualization is and how it works. Once we've done that, we're then going to walk through the evolution of the Nitro project over the last 4 years. We're going to talk a little bit about compatibility and what it means for you as a customer, and then we're going to talk about what we're working on next. When we launched C5 back in early November, we released a set of FAQs, and we included an FAQ about the new hypervisor in the announcement. We actually had a lot to say, but we didn't want to say it during the launch of C5 because there's so much interesting information about it. So instead, we waited for venues like this to really dive deep and explain exactly what's going on under the covers. So what is Nitro? Well, we mentioned that there's a new hypervisor, and really Nitro is the new hypervisor, but it's more than just a hypervisor. It's not just what people typically think of as a hypervisor. So let's take a step back. Before we jump into what the Nitro system is, we really want to talk about what virtualization is. And my main motivation here is really to clarify nomenclature and make sure that when I mention a phrase like device model or virtual machine manager, that we're all saying the same thing. I might be a bit pedantic about it, but people tend to throw around these terms, and I generally disagree with what people say when they're talking about these things. So forget everything you've previously known about virtualization, and let's start from the very beginning. Virtualization is conceptually very straightforward. No matter what, all software, whether it's JavaScript or whether it's a web browser or even the lowest level driver and operating system, consists of a series of instructions that the processor executes. This is typically called assembly code. And no matter what language or framework you're using, eventually it comes down to executing this series of instructions. So the real fundamental question behind virtualization is, if I took the set of instructions that describe an operating system and I tried to run it as a normal application in an existing operating system, say for instance I took the instructions for Ubuntu and then I ran them as an application under Windows, what would happen? Well, let's actually see what happens. So believe it or not, these instructions that are on the screen, this is the beginning of an operating system. These are the first about dozen instructions of the Zen hypervisor. It's not really important that you understand what these instructions are. You don't have to read assembly code to understand what's going on here. For the most part, the instructions do exactly what they say they do. So for instance, a jump instruction just moves the instruction pointer forward by some amount. An add instruction does arithmetic, it does add. It's actually quite straightforward. So what happens if we try to execute the first instruction here? It just works. That's because it's a jump instruction and the processor sees it, and of course it can jump forward by 1 step. It's a little weird to jump forward by 1 step, but there's a very specific reason that an operating system has to do this that we don't really have to talk about here. Well, let's keep going. Let's see what happens when we execute the next instruction. Again, it just worked. In this case, it was a no-op instruction, and a no-op instruction doesn't do anything. So, of course, it works without any real challenges. And again, the next instruction executes without any challenges at all. And so at this point, it's a little concerning because this is all super easy. It's just working. I've mentioned I spent most of my career working in virtualization, so like, what am I getting paid for, right? Okay, well now we hit the next instruction. We've executed 4 instructions and we hit our 5th instruction, and this instruction does not execute properly. So if we took this series of instructions and we ran it under Windows as a normal application, it would actually fail. You'd get an error, and you get an error specifically because of this instruction. Remember, I mentioned that we're running this application as a normal process, and it turns out that there's a series of instructions that you just can't execute as a normal process. All modern operating systems have a notion of privilege levels, and the operating system kernel itself runs in a special privilege level, and as a consequence is able to use instructions that are not available to normal applications. There's actually a formal theory behind virtualization, and what it states is that whenever you encounter an instruction in a lesser privilege level that only is available at higher privileges levels, that instruction has to intercept or trap in order for the processor to be virtualizable. So we hit our instruction that traps, it causes an error, and so then what happens? Well, execution is now transferred to a special component of the system called the virtual machine monitor. And this is really the heart of the virtualization system. The way we respond, the way the VMM responds to the trap is by emulating the instruction. So for instance, in this case, the STI instruction's job is to change a specific flag in a register. That's all it does. And what the VMM does is it emulates that behavior and then returns control back to the underlying processor. So the VMM is really the heart of the hypervisor, but it is not the entirety of the hypervisor. And going back to that theory of virtualization, what that theory states is that as long as the statistical majority of instructions are executing natively, then we call this virtualization. Now, statistical majority sounds like a very complicated term, but really it just means most. And in a typical virtualization system these days, we usually consider that to be anywhere from 1 out of a million to 1 out of a billion instructions are emulated. So the vast majority of instructions are executing directly on the processor, and this is why you get good performance on most modern virtualization systems. Now, while the virtual machine monitor handles emulation of most instructions, it actually can't handle emulation of all instructions. So let's keep going and see what happens. We go to our next instruction and we see, and then we execute another instruction, and this time you get a trap, but this is a very special instruction. This is an in instruction. And the in instruction is one of a series of instructions that's used to communicate with hardware devices. So anytime you're reading from a hard drive or you're speaking to a network device, that's happening through an instruction like the in instruction. And these instructions send messages to other components in the system. One way to think about this is if you're making an RPC call or an API call for a remote web service. In your application, there is some logic to marshal that API call, send it off to the network, receive the response, and then decode it. However, the thing that's implementing the back-end logic might have arbitrary complexity. It might be the entire role of another server or even a fleet of servers if you're talking to something that's sufficiently advanced, like, for instance, the S3 web service. This is very much true with virtualization too. The in instruction itself is relatively simple. However, it might be talking to an arbitrarily complex device on the other end. The key observation here, and the thing that was really the fundamental observation between the Nitro system, is that while we might be executing a statistical majority of instructions natively, the backing implementation of these hardware devices, these virtual hardware devices, is 100% implemented in software. That means that when it comes to optimizing a virtualization system, there's a lot more involved in emulating the hardware than the actual processor itself. So a hypervisor consists of a virtual machine monitor and many of these device models. A typical, the sort of most minimalistic hypervisor will contain at least a dozen device models. However, there are hypervisors out there that actually have hundreds of device models. So really, I think that most of the complexity of a hypervisor really is in these device models itself. But then in addition to a virtual machine monitor and device models, you also have a lot of things that typically come in operating systems, such as a scheduler and a memory manager, control and management services, things of that nature. That said, everything that I've talked to about this point was really state-of-the-art in 1974. I mentioned that there was this canonical paper on virtualization, and that paper was actually published in 1974. So an interesting question is, if we move forward a bit, do a lot of this theory hold out in practice? Well, it turns out that academic theory often doesn't match reality, and if we fast forward to 2006 when EC2 first launched, it turned out that the Intel processors and AMD processors at the time did not actually meet the criteria that was presented in this original paper from the 70s. That said, and this is why virtualization really hadn't caught on in this space until around this time, and that's because there was a project out of the University of Cambridge called Zen that actually found a really clever solution to this problem. So what they did is they took advantage of the fact that a lot of people were running the Linux operating system at the time for which source code is available. And so they went through the source code for Linux and they found all of the instructions that would trap, that weren't trapping properly on modern processors. And they modified them. They turned them into explicit calls, which we now call hypercalls, that would invoke the virtual machine monitor directly. Effectively, they enabled a version of Linux that would meet the criteria necessary to virtualize the system. This technique is called power virtualization. And this is the technique that EC2 originally launched with in 2006. Now that said, it's not surprising that after virtualization began to become very popular on the Intel and AMD processors, that both Intel and AMD implemented proper hardware support for virtualization and introduced new modes of the processor that would trap appropriately, and not only trapped appropriately, but they dramatically reduced the number of times that traps were needed. So today, all new instance types only support another mode that we call HVM, which is hardware-assisted virtualization. And there's lots of performance benefits to it, and largely we recommend all customers use HVM today, such that a lot of our new instance types simply don't support power virtualization anymore. However, if we move forward a little bit, around the time of the first reInvent about 5 years ago, we started to really think about where we wanted to go with virtualization and whether the virtualization stack that really is sort of common and state-of-the-art in the rest of the industry was the best thing for the AWS cloud. And so this brings us to 2012, and we asked ourselves a lot of really fundamental questions. Can we do better than a software-only hypervisor architecture? Most hypervisors are designed to run on whatever hardware you might have in your data centers, but we build our data centers specifically to run EC2. So we can optimize the entire stack all the way down from the physical location to the servers themselves to the software that runs on it. So can we do better given that we're building everything for this singular purpose? Another observation is that these software device models, because they're 100% implemented in software, they compete for CPU and system resources with the actual instances that are running alongside them. This makes it very hard to deliver really good performance, but also to avoid jitter and performance variability. So really what we asked ourselves is, could we take a step back and could we decompose, could we deconstruct the hypervisor, move components around, and end up with something that was fundamentally better for customers as a result? So let's begin the journey that we started in 2012 by taking a look at what we would consider a state-of-the-art instance type from that error. This brings us to the CR1 instance, which I suspect very few people are aware of anymore today, as it's not a very common instance type anymore. This is the predecessor to things like R4 and R3 and our memory optimized instance types. It was actually a really great instance type. It had a lot of really nice innovation in it at the time. It supported 10 gig networking, which was fairly new. It had the most memory you could find in an EC2 instance type. But it was really one of our last instance types that used a purely software hypervisor architecture. And I think I was really proud of what we built for this instance type. I think that even if you take a look at this architecture today and compare it to other virtualization stacks, that I think it still holds its ground against anything else that's out there today. There's a lot involved in getting this architecture right. As you can see, there are a bunch of device models running in software, and they typically run in what's called a control partition, management partition. In the Zen hypervisor, it's typically called a DOM0. And as usually is the case, you run a general purpose operating system because there's a lot of software and you have to manage that software. And we, of course, run Amazon Linux as part of that management partition. It's really complicated to get the device models to run effectively, get the best possible performance, make the best use of hardware, and still deliver as much CPU as possible to instances. So where did we go from here? What was the very first thing that we looked at? Well, the very first thing we looked at was networking. The reason we looked at networking was because networking, generally when speaking about I/O virtualization, is really the hardest problem. And if you're going to do something big and fundamental to your architecture, it's always best to start from the thing that is the most difficult. Because if you start with the easy things, you might get a false sense of what the architecture should be or how things go. If you start with the hardest problem, then you'll learn the most very, very quickly. And so the fundamental question we asked ourselves was, what could we do to get networking out of general purpose software? And this led to the C3 instance type. The C3 instance type was launched in November 2013, and it introduced the very first sort of prototypical Nitro architecture. What we did is we took a commercially available network offload card, and we literally added it to every server. And if you actually had a physical C3 sitting in front of you, you would actually be able to see a loopback cable coming from the normal Intel network card going to this network offload card. It actually looks kind of silly, but it works really, really well. C3 was our fastest growing instance type at the time. We got a lot of tremendous feedback from customers that they loved the increase in performance. C3 had about 20% better bandwidth, but really the thing that was remarkable about this architecture was that we saw a dramatic improvement in jitter and performance variability. So now that there was dedicated hardware for networking processing, we saw really, really consistent performance even at the highest percentiles. So as we typically do things, we love to make small changes, get feedback from customers, and then iterate on top of that. And that's exactly how we've approached the Nitro architecture. So after moving networking off and out of the general purpose management partition, the question is, what is the next piece that we're going to go after? And the next piece of the journey was really looking at storage. So if, again, you're taking the approach of take the hardest problems and go after them first, after networking, storage is the piece of I/O virtualization that takes the most resources, that has the most demanding profile. And so that led us to the C4 instance type. Now, with C4, we again made use of an off-the-shelf component, but this time we started working with a startup called Annapurna Labs. And Annapurna Labs had a hardware network accelerator that had a really unique feature. It had the ability to offload storage and present the offloaded storage as a local NVMe device. Now, at this time, NVMe was actually a relatively new technology. We looked at it, and there wasn't really good widespread support for NVMe within typical AMIs that we would see customers using. So we continued to use a software device model in front of this virtualized NVMe. So from a customer's point of view, the C4 instance felt a lot like a C3 instance, except under the covers, we're actually doing this hardware offload of EBS storage. Again, we saw a really great reduction in jitter and an increase in performance. In fact, the performance improved so much that we were able to make EBS optimized offered by default with no charge. And since all instance types since C4 have also offered EBS optimized performance as part of the default for the platform. So the question is, what comes next? We've offloaded networking and we've offloaded storage, but there is still an opportunity. While this architecture has worked really well for us, we still have a model where we have this loopback cable, and that means that there's an opportunity to improve the overall structure of the platform, reduce latency, and things like that. And so this led to the X1 instance type. And X1 was a monster of an instance type. Even today, even though it's been out for almost a year and a half now, it still is one of the biggest instance types you can find. It was launched with 2 terabytes of memory and 128 vCPUs. But another thing that made the X1 a really interesting platform was that it introduced something called the ENA device. And this is a hardware network interface that we designed specifically for EC2. And this is also around the time where Annapurna Labs became a part of AWS after we acquired them. And we worked together to build a custom ASIC specifically for EC2. And X1 was the first platform where we shipped this new Nitro ASIC that was designed specifically for EC2. And this is what allowed us to introduce the Elastic Network Adapter. One of the things I'll point out at this stage is that there's a pretty steady rhythm here where every 12 to 16 months, we've been iterating on the platform and moving one component around and trying to optimize things. As you can imagine, well, that's how the story is going to continue. And so the next thing that we looked at was instance storage. The X1 platform also included instance storage. Not all of our platforms have included instance storage in the last few years, but the X1 did. And as you can imagine, again, the device models here require lots of software running within the management partition, so it's a prime candidate for offload. This led to the i3 platform. And the i3 platform is another really interesting and exciting platform. The i3 platform is the successor to the i2 platform, which at the time was able to achieve 385,000 IOPS using 8 SSD drives that were available at the time. I can tell you firsthand, there was a lot of engineering work that went into making the software device models work well to be able to drive that performance. It was not easy. It took a lot of work. Well, there's been a change happening in the storage industry. And with the introduction of NVMe, you see an order of magnitude improvement in performance in the actual underlying hardware. So when we looked at something like i3, we knew that we would not be able to achieve that kind of performance purely in software. And so, of course, we continued with the theme, and we used a Nitro ASIC to offload the storage so that when you're actually talking to an NVMe drive on an i3 instance, you're really talking directly to the underlying hardware. So now we've offloaded storage both in the form of instance storage and EBS, and we've offloaded networking in the form of ENA. So what comes next? All of the other software. So we went after the virtual machine monitor itself, and we went after the management partition. We wanted to offload the management partition because we wanted to make those resources available to customers. And for the VMM itself, now that we've gotten to a point where the VMM only really has to do instruction emulation, there really just isn't any need anymore for having a full-blown traditional hypervisor in the stack. And so this is what has led to the C5 instance type and the full Nitro architecture. So the first thing to observe is that in the Nitro architecture, there is no management partition anymore because we're not running software device models on the x86 processors anymore. So when you see 72 vCPUs within a C5 18X large, you have access to all of the underlying physical CPUs. Likewise, you see practically all of the memory that's available on the platform from the C5 18X large itself. Now, when we looked at building the new hypervisor, of course, we wanted to start from a strong established base, and we chose KVM as the base for this new hypervisor because KVM does a really good job of isolating the VMM component from all of the rest of the components in the system. So we really could build a hypervisor with KVM that just consisted of a VMM and didn't consist of all of the other things and baggage that you would typically find in a software-only hypervisor. We like to refer to this hypervisor as a quiescent hypervisor, meaning that it only really runs when you're trying to do something on behalf of the instance. It really only runs when you're doing this trap and emulation. So this leads to a really interesting point in that if the hypervisor really doesn't do that much anymore, do we really even need it? And that's what led us to build the i3.metal instance. So by adding an additional component in the system, namely the Nitro Security processor, we were actually able to implement security entirely in hardware, and that allows us to allow customers to run any workload they'd like directly on the underlying processor without going through a hypervisor. The important thing to point out here is that the I/O devices that you see, the ENA device, the storage devices, those are coming directly from the Nitro card, and they're the same devices that you would see in a C5 instance type 2. This story wouldn't be complete if I didn't mention VMware on AWS. This was actually launched on top of i3.metal back in August of 2017. And uses the same underlying architecture of everything that we've talked about so far to allow customers to run VMware-based software-defined data centers within AWS. So just to summarize, the Nitro system consists of the new Nitro hypervisor, which is a lightweight hypervisor that really just performs the role of the virtual machine monitor. It consists of a series of Nitro cards, which handles storage, networking, management, monitoring, and security. And then the Nitro Security chip, which is integrated into the motherboard and provides physical protection for the system from the very start of execution on the underlying hardware. And so then I mentioned that we would end this talking about what's coming next. Well, as you can see, we like to innovate at a pretty steady pace, and that's exactly how we'll continue doing it. We're already working on the next things, and we're going to continue to release features, get customer feedback, and then iterate based on that. And really, it's the feedback that is the most critical for us, and that's why we do these things incrementally. So I'm very interested in hearing any feedback that you all might have for us, and then and what you think of the C5, M5, and i3 metal instance types. So thank you very much, and I think we are ready to take questions now.